Hello and most welcome to 1190. Yes, now it's time to start with Chris Fields. And I will try to do cross intersection between Chris Fields, Lucio Diego Rappaport during the week. Yes, it would be tough, but now I find that there is access to the both at the same time. It's better to mold the iron when the iron is hot, as we say in Swedish. But be warned, it is quite a handful. This is an article by Chris Fields, Unitary Quantum Theory as a Formal Framework for a Theory of Consciousness. Abstract. If the extraneous and mutually contradictory assumptions of its various interpretations are uniformly rejected, unitary quantum theory provides a clear and self-consistent description of the physical world. The continuing empirical success of unitary quantum theory requires, moreover, that we take this description seriously. The physical world, as described by unitary quantum theory, is globally deterministic, but is provably locally non-deterministic at every scale and from every perspective, definable within the theory. It contains no physically efficacious boundaries, either in physical coordinate space or in Hilbert space. Wow, it's already getting very interesting. Hence, it contains bounded objects or systems only as semantic stipulations that may or may not be useful as physical approximations. Measurable space and time are strictly derivative. In this world, not fundamental. Observer generators of classical information, the kind of information that can be recorded using finite, time-persistent symbols, are ubiquitous to all scales. Like all bounded time-persistent systems, exist only as fiat semantic entities. The physical states of the collections of degrees of freedom constituting observers are mutually correlated by quantum entanglement, but the classical information that they encode is context sensitive in principle. Hence, quantum intersubjectivity is guaranteed. While classical intersubjectivity is at best an approximation. In particular, no classically characterized observation is strictly repeatable. Did you hear that? No classically characterized observation is strictly repeatable. It is argued that the characteristic of classical information predicted by unitary quantum theory, in the absence of extraneous interpretive assumptions, are sufficiently similar prima facie to the characteristics of human phenomenal experience of external objects through either perception or memory, to regard quantum theory as a candidate formal theory of phenomenological object-directed awareness. If viewed in this way, quantum theory immediately entails that structural or functional models of encoding of phenomenal experience by bounded macromolecules, cells, or anatomical systems are at best observer and context relative approximations. Since its inception in the 1920s, quantum theory has been regarded by many prominent physicists and by the vast majority of philosophical commentators on physics as a bare mathematical framework that does not directly describe the physical world. Bohr, for example, is widely quoted as saying, "There is no quantum world. There is only an abstract physical description. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature." While the first, third, and fourth sentences of this statement express an instrumentalist or non-ontic view of quantum theory shared by Bohr, Heisenberg, and many other current researchers. The second sentence expresses the much more broadly held opinion that, unlike classical physics, quantum theory is only an abstract mathematical construct without direct, intuitively clear physical content. As such, it is fundamentally unsatisfactory as a physical theory, regardless of its predicative success. The motivation behind this broadly held opinion that quantum theory is unsatisfactory as a physical theory is clear. We do not directly experience the world as having the properties, such as superposition and entanglement, that quantum theory ascribes to it. We do not experience cats as being both dead and alive, for example, or chairs as being both here and there. Indeed, our ordinary shared pre-theoretical human experience of the world is not even classical in the sense being described by classical physics. It rather conforms to an essentially Aristotelian folk physics that we develop as young children. The world as classical physics describes it is, however, at least close to this intuitive world. The world as quantum theory describes it is not close at all. Both physicists and philosophers have responded to this misalignment between quantum theory and our pre-theoretical physical intuitions by adding assumptions to the theory that make its mathematical predictions more consonant with our everyday experience. The most well-known added assumption is the collapse postulate of von Neumann, 1932, which interprets measurement as an irreversible, non-unitary physical process that converts a quantum state into a classical state. Since the starting point of this non-unitary process cannot be measured even in principle, von Neumann's postulate is widely regarded as a philosophical or interpretive assumption instead of a physical assumption. Indeed, it has recently become commonplace to reformulate it as the claim that measurement converts quantum information into classical information, thus dropping the idea of a physical collapse altogether. Many physicists, however, still regard collapse as a physical process and have developed an enormous diversity of theories to explain how it is implemented. Even the many worlds interpretation of quantum theory generally invokes an objective classical past shared by multiple observers, and hence implicitly incorporates an objective collapse to classicality. The present chapter explores the consequences of an alternative approach to quantum theory, that of taking unitary quantum theory without any added assumption as a literal description of physical reality. There are at least 3 reasons to contemplate doing this. First, unitary quantum theory is both enormously successful and apparently unlimited in its applicability. Increasingly challenging experiments designed to reveal entanglement over macroscopic, spatial, and temporal scales invariably have done so. It seems, therefore, at least worth considering as a possibility that quantum theory might be literally correct in what it is telling us about nature. Second, the assumptions that are added to quantum theory in order to explain the emergence of classicality are invariably classical assumptions. Any explanation of classicality derived from quantum theory, supplemented by such classical assumptions, is clearly circular and hence is not an explanation at all. To take just one example, all models of physical interactions that take the classical boundaries of ordinary objects to be physically significant violate a deep mathematical symmetry of quantum theory and are therefore either strictly approximations or are inconsistent. Finally, what observers and observations are still not understood in physical terms. Some interpreters of quantum theory, most notably van Neumann, gives observers an explicit role in the theory. Most do not. However, the alternative of asking quantum theory itself to characterize observation in physical terms has not been rigorously pursued. Perhaps it should be. In what follows, therefore, I have two main aims. The first is to briefly describe the world in which quantum theory says we live. Bas van Frassen famously asked, how could the world possibly be the way a quantum theory says it is? Perhaps we should examine what quantum theory says and then ask how it could be otherwise. My second aim is to sketch an account of observation within unitary quantum theory, one that draws on the work of Zanardi and others on quantum reference frames and the concept of quantum holography developed by Toft and Susskind. If observation is modeled in this purely quantum theoretical way, our observers are ubiquitous at all scales, and observation is a way of describing what the universe is doing all the times. It is natural in this picture to simply identify consciousness or awareness with physical dynamics, and in particular with quantum entanglement as a resource driving physical dynamics. I conclude by suggesting that this identification of physicality with awareness might be useful both for the understanding what kinds of systems we human beings are and for appreciating the kind of universe that we live in. The world according to quantum theory. let us begin by dropping our preconceived notions of what the world is like and ask what the world would be like if quantum theory, in particular unitary quantum theory with no collapse, was literally correct. This is the question that Everett asked, but the relative state picture that he proposed as an answer did not have the benefit of the last 50 years of work of quantum information, and has been replaced both in physics and in the popular imagination by the many worlds view of a universe that branches outwards from a single past into multiple futures. The many worlds view requires for its coherent formulation not just the classical idea of a bounded object that is persistent through time, but the idea that the same bounded persistent object, e.g. the same individual observer, can exist in and have different outcomes happen to it in different branches of the universe. It is therefore a semi-classical interpretive addition to quantum theory, and not a simple statement on quantum theory as is often advertised, for instance by Tegmark. When not burdened with extraneous classical or semi-classical assumptions, quantum theory provides a remarkably clear picture of the physical world. The key components of this picture are briefly discussed below. Physical dynamics are unitary, and this is crucial in understanding modern quantum theory as a reality. This is what Chris Evans is doing. It has to do with entanglement, and entanglement means that the two things that are connected are actually one thing, and that is the meaning of unitary. A fully entangled universal state is a quantum superposition of all physical possibilities. All possible combinations of the values of all physical degrees of freedom. A fully entangled universe contains no separable systems, and hence contains no systems that evolve independently of any other systems. A fully entangled universe is a universe that evolves through time as a single entity. Indeed, since the state of a fully entangled universe is a superposition of all physical possibilities, its evolution only alters the relative amplitudes of these possibilities. No new possibilities are introduced, nor are any old possibilities removed from the mix. An immediate consequence of unitary is that any closed quantum system, including the universe as a whole, satisfies the fundamental symmetry of decompositional equivalence. The dynamical evolution of any such system is strictly independent of any decomposition of the system into subsystems or part. Formally, decompositional equivalence requires that all tensor product structures, TPSs, of a closed quantum system are strictly dynamically equivalent. This equality of alternative TPSs is an axiom of quantum theory. Axiom 4 is presentation of Nielsen and Chong in 2000. The linearity of the Hamiltonian of any closed quantum system is similarly axiomatic within quantum theory. Decompositional equivalence imposes a powerful constraint on the physics of any system that satisfies this symmetry. That physics cannot depend in any way on subsystem boundaries. Thus, if quantum theory is true of our universe, the boundaries that separate systems within our universe, including the boundaries around observers, are physically irrelevant. Such boundaries are obviously relevant to any description of what is going on, but they are irrelevant to what is going on. This situation can be summarized in a slogan: system boundaries are semantic, not dynamic. It's echoing Ashish Dalela for those who remembers. The semantic nature of system boundaries has significant consequences for both the theory of decoherence and the physical description of observers. These are discussed below. Time is symmetric. Unitary evolution is symmetric in the time parameter t. Indeed, the conjugate operator ut can be viewed as u is universe acting backwards in t. Is, as pointed out by Rovelli 96 and others, t is not an observable in quantum theory. Recordable laboratory time is measured using some other observable, typically position. For example, one measures the position of the hands of the clock or the position of the illuminated segments of an LED display. Measuring time in this way requires that the clock can be singled out as an entity, one that by assumption maintains its identity through time and hence can be repeatedly accessed to make sequential time measurements. This assumption of a time-persistent clock, measurements of which can be recorded in a time-persistent memory, breaks the symmetry of T that is imposed by Unitary. unitarity. From a logical perspective, the assumption that a clock that defines the time maintains its identity over time is clearly circular. More importantly, for the present purposes, this assumption violates decompositional equivalence by defining a boundary. The boundary of the clock that remains inviolate on the unitary transformations. To see this clearly, consider the process by which an observer re-identifies the clock measured previously in order to make a second measurement of time. The second measurement only counts as a second measurement if the very same physical degrees of freedom are measured the second time around. Measuring the very same physical degrees of freedom that were measured previously requires picking them out from among all degrees of freedom of all the universe. No experimental procedure allowed by quantum theory permits doing this. Indeed, any such procedure violates unitarity. As discussed in the more general case below, re-identification of systems, including clocks, as the same things over time is always an approximation. As with system boundaries themselves, such re-identifications are items of classical semantics that are added to quantum theory, not components of quantum theory itself. Once the boundary U that picks out the degrees of freedom of the designated clock is recognized as a semantic boundary and not a dynamic, hence not a physical boundary, it becomes clear that observed time is itself an item of semantics that only appears within the interpretation that defines it, to break the physical symmetry of T. The semantic assumption that defines measured or experienced time is the assumption of identity. Without measured or experienced time, the notion that any system maintains its identity over time cannot be defined, while without the assumption that at least one system, the experiencer or the designated clock, maintains its identity over time, experienced or measured time cannot be defined. The assumption of measured or experienced time and the assumption of identity over time are therefore effectively a single assumption. This assumption is strictly a semantic addition to quantum theory and can have no physical consequences in a world correctly described by quantum theory. Global determinism implies local autonomy. All known microscopic physical interactions, in particular the standard model interactions and gravity, are in isolation fully deterministic. As the Hamiltonian HU, characterizing a quantum theoretic universe, is a linear sum of component interactions, it is fully deterministic if the component interactions are. Explicitly taking decompositional equivalence into account reinforces this conclusion, and by ruling out any higher order interactions that are nonlinear in the fundamental component interactions, and that therefore privilege some TPS over U of others. All evidence supporting unitary quantum theory, therefore, evidence that the evolution of our universe is fully deterministic. But when combined with the universal entanglement, universal determinism yields an interesting and prima facie surprising consequence. The behavior of any given degree of freedom is determined by, but is determined only by, the behavior of all other degrees of freedom in the whole universe. No local collection of degrees of freedom is sufficient to determine any behavior. A deterministic quantum theoretic universe thus satisfies a particularly strong form of the Conway-Cohen free will theorem. The behavior of a given degree of freedom is not only not determined, even stochastically, by the information available in its past light cone. It is not determined by the information available in any local neighborhood, even any local space-like neighborhood. This result is consistent with a recent demonstration that predicting the result of one's own decision-making process under given circumstances has greater computational complexity than simply making the decision, a result that holds whether the decision-making process is deterministic or stochastic, or whether the computational resources available are limited or not. In a quantum theoretic universe, therefore, global determinism implies local autonomy, not only from the perspective of a particular decision-making agent, but from every other local perspective as well. As in the case of system re-identification, local determinism in such a universe is strictly an approximation. These two approximations are strongly coupled. We intuitively expect what we re-identify as the same system to exhibit the same behavior in response to the same causes. This intuitive inference cannot even be formulated within unitary quantum theory without imposing extraneous classical assumptions. Since the development by Zeh and Zurek, the theory of decoherence has become the standard approach to explaining the emergence of classicality within quantum theory. Decoherence is a semantic interpretation, not a physical process. Briefly put, decoherence theory provides methods to calculate the observable quantum states of any physical system that interacts with and is observed from a perspective within a surrounding environment. As a mathematical formalism, decoherence theory is simply an application of quantum theory to the system-environment interaction. Because decoherence theory predicts that the observable states of any system in interaction with the surrounding environment will appear classical to the observers embedded in that environment. It is widely regarded as explaining the apparent classicality of observable states, and hence at solving the notorious measurement problem of quantum theory. But when one examines decoherence calculations closely, however, it becomes immediately clear that the mathematical methods provided by decoherence theory are only applicable in practice when supplemented by classical assumptions. In particular, the interaction between a system and its environment can only be characterized within a TPS that treats the system and environment as components of U. This interaction can only be characterized as a function of time. If the physical degrees of freedom composing the system and those composing the environment are re-identifiable as such over time. As noted earlier, any such assumptions violates decompositional equivalence and is therefore an approximation at best. Decoherence calculations make, in addition, the assumption that the observer obtains no information from the environment. This assumption is often rendered mathematically by assuming that the dynamics of the environment can be treated by using classical statistical mechanical, that is, can be treated as classically random. Again, as noted earlier, do remember this because this is crucial for the understanding. There is no randomness in quantum theory. The assumption of randomness and the use of classical statistics to characterize it is an explicitly classical assumption, as is the underlying assumption that the observer is informationally decoupled from the environment. And that is the tremendous clue. every idea that the observer is decoupled, for instance, that the clock is outside of the universe, will cause classical semantics to enter into the quantum mechanical semantics. Duly noted now, so be observant of this. And this is a classical assumption, as is the underlying assumption that the observer is informationally decoupled from the environment. Making either of these assumptions introduces classicality into the coherence theory, and hence render any explanation of classicality by decoherence circular. Stripped of the classical assumptions of a time-persistent system environment boundary and an informationally decoupled observer, the mathematics of decoherence describes system-environment entanglement, a non-random process that effectively erases any stipulated system-environment boundary. Entanglement with the surrounding environment does not remove quantum coherence from a system. It rather couples the system and the environment in a way that makes their joint state exhibit quantum coherence. Very important as well. What removes coherence in decoherence calculations is the assumption that the observer obtains no information from the environment and hence can treat its state using classical statistics. Sorry. Yeah, I didn't think about that before. It's a surprise, the epiphany. A classically random state is precisely an incoherent state. What decoherence calculations describe, therefore, is not a physical process of coherence removal, but simply the logical consequence of the use of classical statistics to characterize the environmental state. As noted earlier, assumptions of system boundaries are semantic assumptions that are overlaid on the dynamics described by quantum theory. The use of classical statistics to describe the environment depends on the assumption of a system's environment boundary and is therefore itself a semantic assumption. The process of decoherence is therefore a semantic process in which a classical system state and its classical encoding by environment are inferred from an a priori classical assumptions. How great. This is extraordinarily difficult. But what he points to is very similar to the often mentioned discussion between Einstein and Niels Bohr in Brussels at the Solvay conference, where Einstein puts a proof down on the table early in the morning, sometime 1929, 1930, I will get back to the correct year, and all of the supporters of Bohr and Bohr himself are crushed, so to speak, and during the whole day they do not find a solution. What happened? They are almost giving up. But at the night between a Tuesday and a Wednesday, this I remember, the solution comes up. A classical assumption, it was so small, was hiding within the Einsteinian explanation. And the day after, Niels Bohr points that out. That was the last time Einstein ever had any contra-proof to Niels Bohr. Niels Bohr had thereby showed his superiority. But it is incredibly difficult. I would say it's nigh impossible to find where classicality sneaks in. I can promise you, I would never in my life, had I not read this, I would not have understood that by a normal clock, be it a lead clock or an atomic clock, I would not have realized that all of a sudden we take something out of the universe, out of the situation, and we say that this is permanent time. I'm not even sure that that is obvious for Julian Barber. But I realize that directly now. Oh my God, classicality sneaked in. And it has been sneaking in since the Solved conference in dubious ways. It is no protection for classicality to come in. But a clock seems to be part of the universe. It is a part of the universe. And therefore, it cannot be used as a sort of underlying measuring area. It is not a part of a transcendental Tegmarkian otherworldly measuring device of time. It is still a part of the situation, and therefore it cannot be left outside. It cannot be outside to sort of calculate what's happening. It will in that case be just an approximation. Could work, but is no longer true. It's sneaky how classicality in this way can just turn up somewhere. And of course, the discovery is enormous. It is not, well, it's about 9 years. It is Fields, let me get his whole name, C. Fields. I will put it in the description, but I'm completely gobsmacked as it does now. I would never ever have thought of this sort of sneaky way of classicality turning up. And of course, my prognosis here is that classicality is also entered into the Schrödinger cat example. But more about that some other time. I end here and let that sink in. Just put a note where I am. Yes, I have the page. Okay, thank you very much. Thank you for your patience during this 1190 episodes. I think we come to sort of a turn point here. And beware how classicality can sneak in everywhere. It's almost impossible to be aware of it. Okay, thank you very much, and now it's afternoon. I wish you a very pleasant afternoon. Bye bye for now.